Okay, welcome back. So we've talked about algorithms, we've talked about data types and data structures, and sequential data types, list arrays, and that those are also in some ways considered data structures. I showed you a tree of different collections. Now the collections, they're collections of data. And they could be in the form of a data type, they could be in the form of a data structure, but we call them collections because it's a bunch of data all collected together in some form. And we'll go through those as we move forward, but what we're going to hit on in this lesson is the cost associated with the algorithm you choose, different mathematical ways to, we'll say, attack a problem. Now, we've talked before, noted that our focus has to be on not just the fact that our code works, but our code needs to work efficiently and effectively and be scalable. So those are the things that we're going to look at now, and how different algorithms perform. Now, we're going to focus on three different types of algorithms. The first one is called divide and conquer. The second is dynamic programming, which they're all programming, but one's fairly static. We say this is what we're going to do, and then we go do it. Dynamic programming, we say here's the idea, let's go see what happens. And then we've got greedy algorithms, and there's not just one, it's a concept of the goal of the algorithm, or how we go about things. It's greedy. All right. So we're going to start out with what's called a brute force algorithm. Some may call it straightforward. It essentially works like this. We have a problem with the size of n. N being, I don't know how many pieces of data we're going to have to go through. I don't know how big the data set is that we're dealing with. It's n. So our input is of the size n. N can be really, 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 really big. Or it could be kind of small. It could be of the size 10. A brute force algorithm goes through and looks at every item from the beginning to the end of that data set, one at a time, to evaluate it. So let's say we were looking for the biggest value, the greatest value within an array. If the array is 10 long, we start at index 0 and we proceed through it. 0, okay, I know what that is. 1, I compare 0 to 1, and if 1's bigger, all right, now 1's the biggest. I move forward to 2, I compare those. If 2's bigger, I say, oh, all right, now here's our benchmark, or the largest one. And we keep moving forward. And ideally, I would have some variable that I've declared that is the biggest. And as I go through, I do comparisons to what's in biggest to the next index in our array. For us to go through and evaluate that entire array, regardless of how big it is, regardless of the value of n, we have to go through each item one by one by one. Now, do those items have to be in any specific order? No, doesn't matter. We start at the beginning and we go through all of them. Well, what if there's 10 trillion items that we've got to go through? Well, then we got to go through 10 trillion items. So when they say brute force, essentially it means, look, we're going to strong arm our way through everything we got to go through to make sure that we got through all of it. In the example they give, we're visiting all 10 cities. We're going through everything one after another after another. This is the most expensive algorithm because in this algorithm, you have to go in and evaluate every index regardless of what n is, how big this data set is. So this can get very expensive when we're talking about time. It can also get very expensive in terms of, no, not so expensive in terms of RAM, but when n gets very, very big, the amount of RAM we're using can get very big as well. Now, that's what we call brute force. So brute force, if we're talking about big O notation, worst case scenario, yeah, if we pick this brute force algorithm, that's traditionally going to be our worst or least efficient choice. So if I had to compare a brute force algorithm and a divide and conquer algorithm in terms of big O notation, what's the worst case scenario? Brute force is always going to be worst. All right. Now, let's take that exact same data set. Exact same. And the only difference is that for divide and conquer, what I want to do is before I go run this algorithm, I want to run a sort function on the data. I want to sort the data first. So as I go through it for my divide and conquer, I'm going to sort everything that I've got from 0 to n in order. Smallest to biggest, or largest to smallest, it doesn't matter. I sort them. Now I have a data set that is sorted. And my data set that is sorted, well, what I can do now is I say, you know what? I already know that the biggest is at the end. Well, all right. So that example is not going to work. What if we'll change our example and say, you know what? Let's look at this brute force algorithm and say, I want to find a specific value. I want to find the item in this data set that has a value of 256. So think at each one of those indices is a bucket with an index of 0 to n. And in one of those buckets, there's something that has a value of 256. Where it is, I don't know. For me to find which bucket has 256 in it in a brute force scenario, I have to go through one by one by one. Best case scenario, it's in bucket 0, index of 0. Worst case scenario, it's in n. All right. Well, it's randomized, so I don't know where it's at. let's say that, and that's our worst case scenario overall, is going to be brute force. Let's move on to divide and conquer when we're doing a search algorithm. We're trying to find the bucket that has 256 in it. Like I said, we're going to, for divide and conquer, we're going to sort all the values. We're going to sort our data set. We're going to sort it. High to low, low to high, it doesn't matter. So divide and conquer, the logic behind it is, we said, what is n? How long is our data set? It's n. Okay. So if it was 10, we'll start small. Say n is 10. We divide n by 2. That gives us what, 5? Okay. And I say I'm going to look at index 5 and index 5 minus 1. Or I could just look at index 5. Let's go that route. So I'm just going to look at index 5. I say, is index, what's the value in index 5, is it higher or lower than what I'm looking for? What's in index 5 is higher. Okay. Now I'm going to look at indices 0 to 4. Divide it by 2. Divide that 4 by 2, and I have 2. I go look in index 2. It says, what is in index 2, higher or lower? And I keep doing this, cutting the size of the data set that I'm evaluating, the area that I'm looking in, I cut it in half every time I go and do a comparison. Am I above or below what I'm looking for? Oh, I'm below. Now, this is that old game that you may have played when you were young, where you say, all right, I'm going to guess a number. I got a number in my head, and you tell me what the number is. And I'll tell you higher or lower. Logically, if you know the range, or how many numbers out of it could be, I'm going to, in my mind, I got a number from 0 to 100. Okay. Is it 50? You're too high. Well, now I know it's lower than 50. Let me jump in the middle of that set of numbers. Cut it in half. That's the divide part. Cut it in half. Which half is it in? The big half or the little half? Top half or bottom half, however you want to look at it. So we cut it in half, cut it in half, cut it in half. This is so much more efficient than that brute force algorithm. Because depending on what n is, man, the example we had was n equals 10. Worst case scenario, brute force. It takes us 10 times to figure out what the number is, 10 guesses. If we did the same thing in divide and conquer, how many times would it take us? Well, our first guess is 5. Let's say the number that we're looking for is 4. First guess is 5. Now it's lower, so we got one guess. Our second guess is 2. You're too low, so there's 2 guesses out. So now we know it's either 3 or 4. So I'll say, is it 3? No. So it took me 4 guesses. Took me 4 guesses. Best case scenario, how many guesses would it take me? 1. I guessed it the first time. Worst case scenario, how many would it cost me? 4. That's worst case scenario, 4. It's a whole lot better than a worst case scenario of 10. Now, when n gets really, 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 really big, we're cutting it in half each time. And every time we cut it in half, n becomes smaller, becomes smaller, becomes smaller. So this algorithm is so much more efficient than brute force. We just cut it in half and go again, cut it in half, go again. Now, one of the things that you may or may not have been exposed to in a lower level programming language is the concept of recursion. And essentially in recursion, we have a method. We had one that stuff we were looking at before, but let's say I have a method called help. And inside that method, we do an evaluation and we return a value, true or false. And the evaluation that we're looking for is, have we found what we're looking for? And this recursive process, we pass a subset of n to our function. It looks in there and it says, have you found it yet? No. Call the function again and pass it a smaller subset. Did you find it yet? No. Call a smaller subset. See if you found it yet. So instead of having to go through one, go through the other, go through one, I've got the processor working overtime, double time, even more than double time. Because I'm essentially calling this function twice. I can call it twice at the same time. I'm calling it, I'm nesting it. And here's an example. We've got this factorial, we pass it n. And in here, we call factorial again, but we pass it n minus 1. So the subset's one smaller. So if we started out with 4, we return n times, call this n minus 1, we pass factorial 3. It's going to call it, comes down, calls this n minus 2, n minus 1. And each time we're returning back the result of something that hadn't been calculated yet. So this whole thing's got to play out before those values can start getting returned. But we've got this function or this method calling itself. How many times is it going to call? It can't call when that's a 0. N minus 0, it'll pass in 0. But if n is equivalent to 0, return 1. We're done. We've reached the end. So this is recursion. Now, the tricky part about recursion is we've got to be careful that we don't get caught up in an infinite loop. We've got to have mechanisms like this to get out. So what if I had this thing set up and I said, well, define factorial n. And we didn't have this. We just had this return n times factorial n. We have no way out, and it's just going to keep calling itself over and over again and passing that same value to itself over and over again. So we've got to build in something where we're either breaking, we're returning. We've got to have some way to get out of this potentially infinite loop. So it's something that scares folks. Man, I don't want to get in something that is an infinite loop and that I don't even know what's going on. Is it still working, or is it just sitting there spinning and not doing what I think it is? So here's an example of us going through this step by step by step by step, doing recursion. Divide and conquer. I've gone through and talked about it. We've got different algorithms that use this divide and conquer logic. So binary search, that uses the divide and conquer logic, or the divide and conquer paradigm, to where my data set is sorted, and that's the key factor. I need it to be sorted. Need it to be sorted. So that's our thought process, is I've got it sorted, and if I know it's sorted, I can use divide and conquer. Well, what's the cost associated with doing divide and conquer? Performing the sort up front. There's a cost associated with that. How long is that going to take? What's the cost associated with sorting? Depends on how we go about sorting things. Sorting can be done with divide and conquer. Merge sort, quick sort, that's a divide and conquer. So binary search is the example that I gave. We've got this data set. Could be an array, could be a list, doesn't matter. We say, all right, let's get the midpoint. Look above, looking below. We're looking for 4. 14, it's lower. Well, we've got to focus down in the bottom part. Focus down in the bottom part. Focus down in the bottom part. And we end up getting where we're looking for by cutting it in half, cutting in half, cutting in half. So it's 5 long, 3 long, 2 long, 1 long. Keep cutting in half each way. And here's a binary search. Now, binary search has a big O notation of O log of n. So it's a log of n. Log of n is the root of. So when we talk about exponents, like x squared, this is the equivalent of the square root. So the log of n, so we're looking at the root of n. What divided by itself. So merge sort is another type of, it's a sort algorithm, not a search algorithm. It's another type of divide and conquer. All right. So the way this works, we've got our array. So all right, let's cut it in half. We got the lower 4 and the upper 4. Are they in any order? None whatsoever. And we go through and we cut everything in half. All of it got cut in half. Cut high and low in half. Cut those in half. Cut those in half till everything is singular. All right, now let's take these two and let's sort them. Low, high. Let's take these two, we'll sort them. Low, high. These two, low, high. And these two, low, high. All right, we've got that. Let's take these four. Can we look at the highest, is it, well, no, we're going to have to do some juggling here. And these two are going to have to go in between these two. So we end up with 7, 11, 12, 41. Well, how about here? Well, these two are going to go in between these two. There we go. So you're either going in front of, behind, or in the middle, one way or the other. Do the same thing here. So where did these go relative to these? At what point are we putting something in front of and behind? So we know these are sorted and these are sorted. So this is a whole lot easier than going through it, and the comparison is, let's say you're playing cards, whether it's rummy or poker or whatever. People, they sort their cards out, and you hold your cards in front of you, and you start on your left and you work to the right. If you're left-handed or right-handed, it will dictate which direction you go. But you put the lowest on one side and you just start shuffling around until you see that they're all sorted. That's a brute force kind of sort. This way, it's more efficient. We're using the divide and conquer. We cut it in half and manage them individually. These sorts are done at the same time. So I've got this function that does this. The first function says, let's divide. And once we've got them divided, then we start calling the sort. Bring them back together, compare. So divide them, and now bring them together and compare them. Bring them together and compare them. And I have all these things happening at the same time instead of just looking at two, looking at two, looking at two. All of this is happening at the same time. So there's our merge sort. And we've got a cost associated with it. And they say it's O of n times the log of n. So there's the merge sort cost. And they break it down how long it takes or what the costs are for each thing that takes place. And we're doing it recursively, so we've created this function that we keep calling, Now, dynamic programming, this is a different type of algorithm. We're not necessarily using a divide and conquer. What we're doing is we're breaking up the data, and I can essentially use divide and conquer, but I'm looking at, when I break our data set up, I look to the left and I look to the right. It's almost like going down the road. All right, look to the left, look to the right. Which lane are we going to go in? It looks like better odds to stay over in the left-hand lane. I think traffic's going to be easier there. And that's essentially what happens in dynamic programming. It looks one way and it looks the other way. It looks at one half or the other half. And it looks at these two groups and says, all right, which one looks better? I break it into subproblems. And I just say, which one's better? And which one seems better, optimal? And there's statistics that come into play in it. And dynamic programming something that is not as processing heavy, but it's a little heavier on RAM. So this may be a trade-off to get us where we want to be. We think about brute force, man, that's just beating the processor up. Think about divide and conquer, man, I think we're getting good. Now we've got a level of recursion that's taking place in this Fibonacci series that we're talking about to go calculate the Fibonacci number. And we've got recursion along with divide and conquer. That creates our dynamic programming. The end result here, here's the code for it to go through and do it, ends up being 2 to the n, and it's expensive when we're talking about the amount of resources that are running at any given time, but it's efficient at the same time. A whole lot more efficient than that brute force. So the last one we're going to deal with is this greedy algorithms. And greedy algorithms, if you're taking this class because you're at one of the universities, FIU, FAU, FGCU, and they're like, you know, you need to take this to meet your undergrad requirements for your degree program. You're also likely to have to take something like a COT 4400, algorithm analysis and design. You're going to need to really understand what greedy algorithms are. And this is something where you'll get hit with it down the road. So we'll talk about them and then we'll go from there, okay? So a greedy algorithm, essentially what it means is we look at our problem from different perspectives, break it up into smaller pieces, and we say, all right, I tried this, I tried that, I tried another solution, and I tried those solutions on these little subsets, if you will. And I came up with what I thought was overall the best solution. It may not be the best solution, but based on the logic that I applied and the process I went through, well, this is the best for how we went through it. And that's the greedy aspect of it. So let's go through and we'll look at, let's say, the shortest path problem. So in the shortest path problem, and we're going to be dealing with logic that will be applied to graphs in this instance. A knapsack and shortest path are both graph problems, how to apply an algorithm to a specific data structure. So in this, we're looking for the shortest route. Now, let's say that, and I want to put this in the context of something that we've all seen. You order something on Amazon. They have software that applies an algorithm to determine the most efficient route, the shortest path, for the delivery driver, given the stops they have to make. Shortest path problem. We need to find the shortest possible route to deliver all those packages. I want to get in, get it done, and minimize the amount of gas, the amount of time, So I need an algorithm that will do that. That's what this is. Okay. So we start out and we say, here's all the stops we got to make. Where are you starting at? I'm starting at this node right here. Okay. And you need to visit all of the nodes? Yep, all of them. So what this essentially is going to do is look at, from that first node, what the closest nodes are. Which one's closest? That one. All right, let's go to that one first. All right, what's the closest? And we mark that one off as I've been there. I've delivered that package, or that node has been visited. Now I go to the next one. Closest, visited. Next one closest, visited. So I go through step by step by step until they've all been visited. It went through and determined which one was which and which ones I needed to go to first. Now, here's a graph, and when we look at it, let's say we start at node A. I say, all right, are we going to node B or are we going to node E? The distance between A and B is 5, or the cost associated with A to B is 5. Cost associated with A to E is 2. Cost associated from A to D is 9. Oof, well, that's easy. I'm going A to E. Check that one off. I've already been there. That one's checked off. Well, I gotta go this way. Boom. I gotta go this way. Boom. I don't have to go that way. I've already been there. Boom, boom. So it costs me 2, 5, 7, 10, 12. There's a path. And we can go through and look at the alternatives and say, well, what if I went to B? I've only can go over here. I can do the math on what ends up happening if I go that way. I can do the math of what happens if I go this way. So there's only so many options that I have. Given that this is a weighted graph, we figure out the weights and we pick the smallest weight. If it wasn't weighted, we'd go down each one and then we'd see how long did it take. So that's another way to look at what it is we're going at. Okay. So this is the greedy one. And I don't want to drive far. I just want to take the shortest path. That's the shortest. Go that way then. Meaning greedy. I don't want to waste gas wandering around. Let's just get to the next one. Let's get to the next one. That's the logic that's taking place here in this greedy algorithm. Okay. We can look at it from, there's cost associated with the path. There's a value associated with getting to that node. Whatever it may be, we've got different things that we can use to evaluate how we're evaluating the path from one node to the next. And it all boils down to greed. I do not want to waste resources, and I want to get the biggest bang for my buck, if you will. Okay. So that's the gist of what we're looking at when we're talking about the different types of algorithms. Okay. And they go through and explain, we've got dynamic, we've got divide and conquer, and they're similar. We've got the concept of recursion. That can be a costly thing that we deal with if we're not careful about how we're using recursion. We've got the greedy approach. See, in that one, at each step of the algorithm, the best choice is taken. And hopefully that ends up giving us the overall most efficient way. It doesn't always, but based on the path that we took and what we knew, it was the best I could have done given what I knew. Now I know it may not have been the best way to go. Go through and evaluate these. Answers are back at the appendix. Okay? And I will see you in another lesson.